Welcome. We have now finished looking at microscopic balances, but we had looked at only for laminar flows and non-Newtonian flows. But we still had laminar flow there. We still had we did not consider turbulence there. Now in this lecture and the next one, what we are going to look at is more about turbulent flow. Just to get you started, this is where we are with respect to the course. We are on part 7, basics of turbulent flows. We are going to look at it very briefly. Okay, so it's only 4 lectures that we are going to look at very briefly. Before we go forward, just revise what you mean by a Newtonian fluid, non-Newtonian fluid. What are the various types of non-Newtonian fluids? What is meant by apparent viscosity? What are the various viscometers available to measure the rheology? Okay, revise that so you are familiar. Revise Navier-Stokes equation, equation of motion, equation of continuity. See the problems that we did once again. Okay. Let's start now talking about turbulent flows. Okay, so first of all, recall the video that we saw when we were talking about turbulent flow. Do you recall that we had talked about turbulent flow? I had shown you a video of turbulent flow in pipe. Look at the first lecture. Here is that video again. You see how rapidly the velocities are changing. How rapidly velocities are changing. This is a real-time video. It's not fast forwarded. It's a real-time video. You see how rapidly these viscous velocities are changing. You see how rapidly the velocities are fluctuating. Okay. That's the point I want you to note. In a turbulent flow, velocities are changing very rapidly with respect to time. Okay. That's an important point, and we are going to talk about that more and more. So what we will do is imagine that there is a pipe flow and we plot at any point in that pipe that you saw, any point, any one point. So if this is a pipe, let's draw a pipe. Yeah, so let's say there is a pipe like I should draw nice pipes. Yeah, so imagine that there is a pipe like this and flow is occurring from left to right. Flow is turbulent. We are looking at any one point in the pipe, and at that point we are plotting velocity as a function of time. Velocity as a function of time. Look at the scale, milliseconds. Although I don't have values, but it is in milliseconds. Right? Velocity, you will find it fluctuates, it changes. So the velocity at any instant of time, here or here or here or here or here or here or here, any instant of time is called as instantaneous velocity. Let's write that instantaneous velocity by a symbol u. Okay. We can also do a time averaging and calculate the time averaged velocity at this point. It is not the cross-sectional average. It is not flow rate divided by cross-sectional area. We are looking at time averaged velocity at one location. So if you take average of all of this, let's say it is like this red line, time average. We are going to call this as capital U if you want, or a capital V for velocity. So that's called as a mean velocity. Mean, it doesn't mean average. Mean means it is averaged. Mean doesn't mean cross-sectional average. Mean means it is time averaged. Time averaged. Averaged over time at any location. Time averaged. Not cross-sectional average. It is not Q divided by half rho V square. It is velocity time average. This is that red line. and any instantaneous velocity we can decompose as, or decouple or write as capital U plus U prime. U prime. U prime, we are going to call this as fluctuating velocity. Fluctuating velocity. Fluctuating velocity. So this fluctuating velocity is telling you what is the level of fluctuation over this time average velocity at one location. Okay? It's an indication of all these packets of fluid arriving and going from that point. It is an indication of the different packets of fluid which are arriving or going from this point. These packets of fluid we are going to call as eddies. One eddy, multiple eddies. These are like swirling motion, vortices. They are like eddies. Okay. So in a turbulent flow, we can characterize a turbulent flow by presence of eddies, which go very rapidly from one location to another location, and they have a lot of velocities. Their velocities can be significantly different from the time average velocity. So for example, time average velocity here is like point, this is like minus point like half if you want, 0.007. But look at this instant, velocity is positive, not negative. Velocity is positive, it is in the other direction. Here velocity is significantly lesser, significantly more negative. So mean velocity is negative, minus 0.007, let's say, but the instantaneous velocities can be positive, or they can be very large negative values, 3 or 4 times this number. Is 3 or 4 times in this number. Magnitude is also 3, magnitude is 3 and 4 times, 3 or 4 times, and value is, the direction is opposite. So these eddies have very large velocities, and they go from one point to another point, or they are packets of fluid which are moving in a turbulent flow very, very rapidly. That is what characterizes the turbulence. Now what we have to do is characterize how much is the momentum transfer arising out of these eddies. Before we do that, we need to talk a little bit more about what these eddies are, what are their sizes, what is their length, how long do they take to travel from one place to another place. Okay, so there is a hypothesis in turbulence made by this person called as Kolmogorov. So whenever you see a flow, turbulent flow, this person proposed that the turbulence is generated because we are dissipating energy, we are generating momentum arising out of delta P or arising out of gravity or whatever it is, or maybe agitation. We are generating momentum by dissipating some power. Power could be in the form of a pump, pressure drop multiplied by volumetric flow rate, or it could be the agitator motor power. Some way we are agitating the fluid, the amount of energy that we are giving that fluid decides how much turbulence we are having. So this person categorized the amount of energy that we put in as power dissipated per unit mass. Okay, it denoted it by epsilon. So what he has said is, if power dissipated per unit mass is small, I'm generating very small momentum, I'm giving small amount of energy to the fluid, flow could be laminar. And as I keep on giving more and more power per unit mass of that fluid, I keep on agitating more, I will get turbulence. So this power per unit mass unit is of course watts per kg. Watts we can write as joules per second. right? And joules we can write as Newton meter, and newtons we can write as kg meter per second square, right? So this watts we are written as Newton meter per second, that kg is there, kg, and Newton we have written as kg meter per second square. This meter is there, this denominator second is there, kg is there, right? So now kg cancels out. Epsilon has units of meter square per second cube. Now he said that this is what is driving the turbulence, this is what is causing the turbulence. What is dampening or preventing turbulence? Viscosity. More viscous the fluid, it will be laminar flow. Less viscous the fluid, it will be turbulent. So characterize the viscosity by a term, kinematic viscosity, mu by rho, and we have seen units of that. Mu by rho is like momentum diffusivity, it is like meter square per second. So higher the diffusivity, lower is the turbulence. Lower the diffusivity, higher is the turbulence. So now this Kolmogorov made different scales using these two sets of units, meter square per second cube and meter square per second, and he defined those as the smallest eddies that are present in the flow. Let me tell you why smallest eddies. Okay, just be patient. So first of all, he said Kolmogorov length scale. Now how do I get length scale from a unit of meter square per second cube and meter square per second? Well, if I multiply them together, I will get meter raised to 4, second raised to 4, 1/4 power of that. That will give me a velocity square, right? So velocity scale is nu multiplied by epsilon raised to 1/4. Let me write that once again. This is the same as nu into epsilon raised to 1/4. If you do divide nu by epsilon, what will you get? Divide this meter square per second cube by meter square per second. I will have second meter square per second divided by meter square per second cube. I will have second raised to half. Take square root of that, we will get a time scale. So time scale is nu by epsilon whole thing raised to half. And if you take nu cube by epsilon, cube of this divided by cube of this nu cube divided by epsilon meter square per second cube, then we will get a length scale. We will calculate all these values. Just bear with me for a second, just till we calculate. Not second, just few minutes. We will calculate raised to 1/4. Now, when we calculate Reynolds number, remember what Reynolds number is? Reynolds number is dV rho by mu. But we are taking this dV rho by mu, but I could take any length scale. Say for example, when we are talking about solid particle settling, we took Reynolds number based on particle diameter. We took based on terminal velocity, right? So any length scale we can take and any velocity scale we can take. So I can generate a Reynolds number based on length scale, Kolmogorov length scale, Kolmogorov velocity scale, and mu by rho kinematic viscosity. And if you put these expressions, let's put these expressions, right? Kinematic viscosity, eta, the colmograph length scale is nu cube by epsilon, raised to 1 by 4 multiplied by velocity. Velocity is nu into epsilon raised to 1 by 4 divided by mu by rho nu. That's our Reynolds number for the colmograph scale, REK. And you will see epsilon cancels out, it is nu cube, nu raised to 1 by 4, 1 by 4. So I will get this equal to 1. So colmograph Reynolds number is 1. That means Reynolds number for the colmograph scale eddies is 1. These are the smallest eddies that are present. Why? Because anything less than 1, it will be laminar flow. These are the smallest eddies that are there in the turbulent flow. Smallest eddies. These are the smallest scales. Largest scales are like the large eddies. They are of the order of the size of the equipment. Right? For example, if it's a pipe flow, the largest eddy will be of the order of pipe diameter. Velocity of the large eddy will be of the order of the velocity of the fluid. Right? Those are the largest eddies which cause a lot of fluctuations. Lots of fluctuations. You see, these are big fluctuations, and there are small fluctuations as well. Small fluctuations. Small fluctuations. And there are big fluctuations. Like this whole thing is a big fluctuation. Okay. So if you have a large eddy, it will have a kinetic energy proportional to u square, and it will have a time scale of L by U. So the hypothesis is, just let me tell you this time scale as L by U. So imagine if you are standing on a platform, there is a train of length 100 meters and the train is going at a speed of 10 meters per second. The train will pass you in 100 divided by 10, which means 10 seconds. So length divided by velocity gives you a time scale. So what the hypothesis is, all the kinetic energy of this big eddy is dissipated in one lifetime. So kinetic energy is u square, one lifetime is L by U. So the rate at which energy is dissipated is u cube by L. That's the hypothesis. So this energy that is being dissipated, it is dissipated because it is dissipating, the big eddies are dissipating energy in one lifetime. One lifetime is L by U, length of the big eddies divided by U. This is not an equal to sign, it is only an of the order of magnitude sign. It's not an exact number. Now, can I take this eta by L? That will tell me what is the ratio of the smallest eddy to the largest eddy. Rework this maths and you will find that this eta by L, do this maths for yourself, eta by L is proportional to eta by L. Let me write this as L. Let me write L properly. Eta by L. Eta by L is proportional to or is of the same order as Re based on L. Re based on L means large scale Reynolds number, like the pipe Reynolds number, raised to minus 3 by 4. Means higher the pipe Reynolds number, smaller will be the colmograph scale. That is the meaning of this expression. Higher the Reynolds number, let's say higher the pipe Reynolds number, smaller will be this colmograph scale. Eddies are smaller and smaller and smaller, the higher and higher Reynolds number I get. That means the spectrum between the smallest eddy and the largest eddy is going to be bigger and bigger and bigger as we go to higher and higher Reynolds number. If Reynolds number is small, the spectrum is just zero, flow is laminar. Okay. Higher the Reynolds number, larger and larger is the spectrum. And that spectrum of the eddy sizes is something to do with these fluctuations. higher and higher the Reynolds number, you will have more and more fluctuations. That's why recall the video that I showed you in the first class. We had a transition flow and we had turbulent flow. Transition flow, sometimes it was laminar, sometimes it was turbulent. The size of the eddies were not very big. Spectrum between eta and L not very large. But as you go to higher and higher turbulence, the video that I showed you in this lecture, fluctuations are very rapid. The spectrum of eddy sizes between the smallest and the largest is very, very big. Let's go forward. Let's try to estimate these values. Okay, so here is an example just so that you are fairly comfortable with all these things. Let's say pipe diameter is 2 centimeters. So D is 0.02 meters. Velocity is 2 meters per second. Rho is 1000, mu is 10 raised to minus 3. So Reynolds number in the pipe, dV rho by mu, this U is the average velocity, cross section averaged, is 4 into 10 raised to 4. Friction factor is 0.046, Re raised to minus 0.2. Let's say it's a smooth pipe, 0.005525. Delta P we can calculate, 2F rho V square, V average it is, square by D, delta P by L. You will get delta P from there. Flow rate is pi by 4 D square multiplied by V average. Calculate this. Do these calculations yourself. Values are given, but you do yourself and make sure that you get these values. So mass per unit length of the pipe is pi by 4 D square L multiplied by rho divided by L. That will tell you 3.142 kg per meter. Power per unit length is volumetric flow rate multiplied by delta P by L, 1.389 watt per meter. And energy dissipation rate, epsilon, you will find is now 4.4 watts per kg. It is same as 4.4 meters square per second cube. Meter square per second cube. Okay. Calculate Kolmogorov length scales now. Kolmogorov length scale would be 2.185 into 10 raised to minus 5. 21 microns. This is like 21 microns. Do this for yourself, only then go forward. Time scale would be 4 into 10 raised to minus 4, so 0.48 milliseconds. That's how fast these eddies are moving. This is the size of the smallest eddies. This is how fast they are arriving, and their velocities are 4.5 to 10 raised to minus 2, 4.5 centimeters per second, or 4.6 centimeters per second. That's the kind of velocities that the smallest eddies have. What is the largest eddy? Largest eddy is typically, let's say, type size of the pipe 2 centimeters, or radius of the pipe 1 centimeter. Velocity is like the average velocity, 2 meters per second. So you see, velocity of the eddies is between 4.6 centimeters per second to 2 meters per second. So eddies are of all these velocities. Sizes of the eddies are like 1 centimeter to 21 micron. That is the size variation. You see these fluctuations as well. Sometimes these fluctuations are very quick, very rapid. Small eddy has come and gone. Sometimes they are over a gradual. You see, there is a gradual change from here to here. Big eddy. Length is big, change of velocity is also big. Right? Okay, so this is just to tell you how to calculate these values for yourself. Okay. Now we talk about, when we talked about when we derived stress terms, viscosity, effect of viscosity, molecular motion, same way we are going to do. Let's assume that there is a velocity profile Vx, Vx is changing in the y direction, right? What does that mean? dvx by dy is non-zero, right? Do you recall? dvx by dy, vx is changing with respect to y. dvx by dy is non-zero. So what did we do? We talked about mass of the molecule. Now I have to talk about mass of the eddy. When we derived laminar flow, we said molecular motion. Now I have to think about eddy motion. And this eddy, let's say, has a certain velocity in the y direction given by Vy prime. How much momentum this eddy has per unit volume? It is rho into ux at location 1. When it goes to location 2, how much extra momentum or how much momentum deficit it is bringing? ux1 minus ux2, rho into ux1 minus ux2. That is the transfer of momentum because of one eddy, and all these eddies are moving. That is going to result into a velocity in the y direction, but it is only a fluctuating. It is only for some instant of time. Average time average value is 0, but it is only at that some instant of time some eddies are taking. So one such eddy is taking. So uy therefore prime fluctuating, and velocity is nothing. Uy prime is nothing but velocity is nothing but flow rate per unit area. So this is like rate of change of momentum per unit area. It is rate of momentum transfer per unit area, nothing but force. So it is force per unit area acting on this plane at y equal to 2. This plane. Okay. And that force is in the x direction because it's the x momentum that we are talking about. So therefore we are going to call it as a stress. It is like tau yx, but it is not because of molecular motion. It is now stress tau ix because of turbulence. Let's call it as tau ix t if you want, for turbulent stress. Okay, simplified. ux1 I can write it as mean, means time average plus fluctuating. ux2 time average plus fluctuating. Bring the mean part here, keep the fluctuating part here. If I neglect the fluctuating part right now, I will just get rho ui prime ux1 minus ux2. Now I can do a Taylor series expansion for ux2. Taylor series expansion for ux2 would be ux1 plus y divided by 1 y du by dx, du by dy, plus y square by 2 factorial dux by dy, and so on and so forth. This will cancel out. We are neglecting higher order terms. All such higher order terms you neglect. So you will find that the turbulent stress is rho ui prime y dux by dy. This is now the strain, mean velocity, strain, but it is at a local value. It is a time average strain at that location. Strain. So this now is our stress strain relationship, constitutive equation. This is our viscosity, but it is viscosity not arising out of molecular motion. It is viscosity arising out of eddies. We call this as turbulent viscosity. Okay, let's go forward. Think about this. This is called as a Prandtl mixing length theory. Eddies are traveling over a distance y, and they mix and they transfer momentum. That's the meaning of this mixing length theory. Okay, just to recap, turbulent viscosity is rho ui prime y. Turbulent diffusivity, if I divide this by rho, bring the rho on the left side, it will be ui prime into y. Recall, for molecular transfer, kinematic viscosity was u into lambda. This was RMS velocity of molecules, and this was mean free path between the molecules. Forget that 1 by 3 and all that just now. Just write it as an order of magnitude if you want. Now this is an eddy velocity and distance over which eddies travel before they mix with each other. Length scale of eddies. How much distance do they traverse? Again, typical example, if I take mu t as rho 1000, right, from here 1000, u prime eddy velocity, let's say 10% of the cross sectional average velocity, 10% of 2 meters per second, this example 10% of this, just some location, just to know why. 10% of the pipe radius, diameter is 2 centimeters, 0.02 meters, radius is 0.01 meters, 10% of the radius, 10% of 0.01, you will find that the viscosity is 0.2 pascal per second, 0.2 pascal second, whereas viscosity of water is 0.001 pascal second. The ratio of eddy viscosity to molecular viscosity is factor of 200. Transport of momentum by eddies is 200 times faster or 200 times more rapid than by viscous transport. So we need to account for this in our equation of motion. When we derived Navier-Stokes equation, we had considered convective forces, pressure forces, gravitational forces, viscous forces. Now this is an extra force arising out of motion of eddies, extra stress, which we need to account for because it is significantly larger than the molecular transport. Here is how we are going to do. So when we had laminar flow, what did we write? Our equation of motion or Navier-Stokes equation for constant density and viscous and Newtonian fluid. This was the Navier-Stokes equation in the vector notation. Recall, go back to that lecture, see for yourself. Turbulent flow, now we are going to have the same. This is going to be the same. Convective transport is going to be the same. Pressure force is going to be the same. Gravity force is the same. Viscous force is going to be the same. We are going to have to add this one extra term corresponding to turbulent transport or turbulent viscosity, and this term is significantly large as compared to this. So it is not that this term is negligible, I can neglect. And mu t, where is it coming from? It is coming from size of the eddy, it is coming from velocity of the eddy. Therefore, it is not a physical property, it varies with the eddy sizes that are there at that particular location. So it will change with the location, it can change with time as well. It's not a property of the fluid, it is varying in 3 dimensions. So when we did laminar flow problems, we could simplify and get it into 1 dimensional. So we could, instead of writing partial differentials, we wrote it as total differential. We had only a second order differential equation. But now we are going to have to solve all the 3 directions simultaneously because eddies can go from one direction to another direction as well. If I have eddy moving here, it can go to y direction, it can go to z direction. It will lead to significant values of mu t in all the directions. And this mu t can be direction dependent as well. Mu t at same location, it is not isotropic. At the same location, mu t can be different in different directions. Mu t in x direction can be different, y direction can be different, z direction can be different. Because the eddies that are there in x, y and z direction, how they are moving, they need not be identical. So these are very complicated equations. So we need to describe first of all how this mu t changes with the local flow velocities or local velocity fields, pressure field, velocity field. And these are called as turbulence models. Extra mathematical models, equations are required. Either they could be algebraic equations or they could be partial differential equations. These are called as turbulence models. Turbulence models are mathematical equations which describe how mu t varies with velocity or pressure or something else. Local energy, local epsilon. So, and we need a numerical solution for this. Okay, so pause the video, make sure you got understood everything so far. We'll go forward now. We will apply this to a turbulent pipe flow. So imagine that there is a pipe here. Pipe is straight. So imagine that there is a pipe. Imagine that there is a pipe. Right? Flow is occurring from, let's say, left to right. This is the center line of the pipe. What we are looking at is we are looking at flow near the wall. We are looking at flow near the wall. We are looking at flow here. And we are looking at a narrow region, therefore the curvature we can neglect. We will replace it by a Cartesian coordinate system, x coordinate and a y coordinate. And look at the velocity field. Remember the velocity field? Velocity field was like this, something like this, 1/7 power law model. You recall? So near the wall, velocities are small. If velocities are small, can we say Reynolds number is small? Local Reynolds number, AD Reynolds number if you like, it's like 1, right? So your flow is laminar there. So near the wall, this is the wall of the pipe. This is the wall of the pipe, bottom wall of the pipe. Near the wall of the pipe, flow is laminar. We call that as viscous sublayer. Viscous sublayer. But away from the pipe, there is a lot of turbulence. So we call this as a turbulent core. And in between, there is a region, there is a gray zone where sometimes flow is laminar, sometimes eddies are there, like a transition region. We call this as a buffer layer. Okay. Now let's try to derive some equations for these layers and then we can calculate something based on them as well. Okay. So in the viscous sublayer, what are we going to say? Eddies are absent, right? So here mu t is 0. Okay. And flow is nearly one directional. So we can say mu dvx by dy. Now there's no minus sign. Vx is increasing with y. This is the velocity profile. Velocity is 0. Velocity is high. Velocity is increasing with the y direction. So you can say mu dvx by dy is tau w. We are going to define a couple of things. We'll see why do we define that, but let's define them just now. We are going to define v star as a friction velocity. Okay, it's a characteristic of the friction that is occurring. So we will say tau w is defined such that rho v star square. So if I substitute that here, mu dvx by dy rho v star square. This is the first order differential equation. Integrate y equal to 0, vx is 0. So vx you will get as divided by mu, vx will be rho v star square y by mu, or vx by v star we can write it as y rho v star by mu. Doesn't this look like a Reynolds number? So vx by v star is a dimensionless number. Doesn't the right hand side look like a Reynolds number to you? It is a Reynolds number based on y and v star. Remember our Reynolds number was any length scale here the length scale is y. Any velocity scale, here the velocity scale is v star and rho by mu. So we are going to call this dimensionless velocity as Vx plus, and this dimensionless distance y we are going to call as y plus. So our velocity profile in the laminar flow, in the laminar sublayer or viscous sublayer, is Vx plus is equal to y plus, and experimentally it is observed that this is valid till a y plus of 5. Okay. Let's go to the buffer layer. We are just outside the viscous sublayer. Okay, but now eddies have started forming. If eddies have started forming, then we can say this nu t is large. Kinematic viscosity, eddy viscosity is large. Dynamic viscosity is small. We can neglect this as compared to this. So we can say the stress is because of the eddy motion. It is mu t dvx by dy is equal to tau w, because we are still close to wall. Stress is still equal to almost tau w. Recall how the stress was in a pipe flow. If this was a pipe and our stress profile, if you want to draw, this is the center line. Stress profile was like this. Stress was 0 at the center, stress was tau w at the wall, and we are at the viscous sublayer, edge of the viscous sublayer in the buffer layer. Stress is still almost like tau w. So mu t dvx by dy is almost like rho v star square. It's almost like tau w. And mu t we can assume as a velocity, rho velocity scale and a length scale. Rho velocity scale, some average, like mu t, rho should be there, right? So rho should be there. Rho should be there. Mu t is a, or you can say that constant a prime takes care of that density, right? V star and y. Substitute that a v stars y dvx by dy is rho v star square. Okay. Cancel one v star. Y is there, a prime y dvx by dy is rho v star. Bring this v star here, dy by y here, rho by a. Integrate from 0, edge of the viscous sublayer, velocity is still very small. It is almost 0. The lower side of the integral is still almost 0. Vx by v star, rho by a, ln y plus some constant v. So the velocity profile, if we can make it dimensionless with respect to y plus and v plus, is given as v plus is equal to a log y plus b, some constants. And experimentally we find that this buffer layer is valid up to a y plus distance of 30. So between y plus of 5 and up to 30, this expression is valid. It is experimentally observed. This relationship is experimentally fitted. The values of constants are experimentally obtained. In the turbulent core, just the same velocity profile is continued, but a different constant, because now it is more and more turbulent. Okay. So this is called as universal velocity profile, because it is applicable wherever there is a plate or wherever there is a surface and there is turbulence above the surface. It could be pipe, it could be flat plate, it could be aircraft, it could be a stirred tank, wall of the stirred tank which is a flat plate and where flow is there. Everywhere this is applicable. That's why it is called as universal velocity profile. That's why it is talked in terms of Vx plus and y plus. It is talked in terms of friction velocity, not in terms of the specific geometry of the pipe or jet or aircraft and things like that. Just some typical values, let's calculate. Tau w is f multiplied by half rho v average square. It is also defined as rho v star square. So v star friction velocity would be v average square root f by 2. Now you know why we are calling this as friction velocity, because it is characterizing the friction factor. So take our previous example. D was 0.02, V average was 2, F was 0.0055, delta P by L was 2210, Pascal per meter, tau W was 11.05. V star would be 2, V average square root F by 2. V star would be 0.1 meter per second. Y plus would be Y rho V star by mu, rho is 1000, 0.1, 10 raised to minus 3. So Y plus is equal to 10 raised to 5 into Y. Now we want to find out what is the thickness of the laminar sublayer. Thickness of the laminar sublayer is Y plus equal to 5. Y plus equal to 5 would mean from this expression Y would be 50 microns. Edge of the buffer layer is Y plus of 30, which means Y of 300 microns. Pipe radius is 1 centimeter. So if I put 1 centimeter 0.01 meters there, Y plus would be 1000 or 10 raised to 5 into 0.01. 10 raised to 5 into Y, so 1000. It will be 1000. 1 centimeter is 10,000 microns, which will correspond to Y plus of 1000. So now you see how small this viscous sublayer and this buffer layer are. Pipe is 10,000 microns. Viscous sublayer is 50 microns. Viscous sublayer plus buffer layer is 300 microns. Or if you want to talk in terms of Y plus, center line is Y plus of 1000. Center line is Y plus of 1000. Viscous sublayer is Y plus of 5. Buffer layer is edge 30. So from 30 to 1000 is turbulent core. You can see almost practically everything is turbulent core. Okay, just very quickly. In the turbulent core, what is the expression that we have? Vx plus is 2.5 ln y plus 5.5. That's the expression that I have written. At the center of pipe, what can we write? Vc plus x is just equal to, we are just writing in terms of the center of the pipe. 2.5 ln y at the center of the pipe. Substitute. Vc plus is nothing but Vc, that is the center line velocity, divided by V star. 2.5 ln y rho V star by mu. Y is now radius of the pipe, so it is R, radius of the pipe. R rho V star is V average root F by 2 mu. Vc is Vc by V star, Vc V average root F by 2. Look at this expression. Look at this expression. Forget about density, R, V average. These are just some constants for a given geometry. You will find this equation is of the form 1 by root F is A ln Re root F plus B. Hadn't we seen this kind of equation earlier? We had called this as Holbrook equation to derive how friction factor is related to Reynolds number. You see what we are trying to drive at. This is the experimental data for universal velocity profile plotted in terms of V plus and Y plus. So up to 5, you see Y plus of up to 5. It is viscous sublayer up to this. Up to 30, 20, 30, up to here. This is buffer layer. This is viscous sublayer. This is buffer layer. And our turbulent core is here. These data points that you see, they are data from different people's experiments. People have actually experimentally measured how Vz changes with Y using pitot tubes and hot wire anemometry and things like that. Let's not get into that, but these are data for different fluids as well as for different people, air, water, as well as different people in their different experimental setups, different pipes, different flat plates. All data behaves in the same way, universal velocity. That's why it is called as universal velocity profile. What are we trying to say? What we are trying to say is, if I know how mu t behaves, how turbulent viscosity behaves, I can use this expression, I can solve and even get up to friction factor versus Reynolds number kind of relationship. Although we have not got the exact relationship, just more maths that is to be done, but we can derive the functional form of that relationship, starting from equation of motion, starting from microscopic balance. This is a microscopic balance for turbulent flow. We can get things like friction factor, like velocity profile. Point that I'm trying to make is all the macroscopic quantities, friction factor, pressure drop, tau W, drag, lift, C0, orifice discharge coefficient, CV, venturi discharge coefficient, drag coefficient, lift coefficient. uh, all those things can be calculated based on microscopic momentum balance. Microscopic momentum balance. I don't have to resort to empiricism. I don't have to wait. I don't have to look at some friction factor. Somebody will give me the friction factor. I can calculate everything for based on microscopic balance. That's the point that I'm trying to drive at. That's the point that I'm trying to drive at. We don't need macroscopic balances if we start doing microscopic balances and integrating those microscopic balances to the sizes of the objects. We don't need macroscopic quantities. All the first 5 parts you can forget. Do everything based on microscopic balances for laminar flow as well as turbulent flow. That's the point that I'm driving at. That's the beauty of microscopic balances. That's the applicability. That's the power of Navier-Stokes equations. That's the power of turbulent flows. That's the power of modeling turbulent flows. We can predict everything that we want. Next class, I will show you some more examples of what I'm really meaning. What we have discussed in this class is from chapter 5 of Bird Stewart Lightfoot's book. We are looking at sections 5.1, 5.3, 5.5. Solve the problems 5a.1, 5a.2, 5b.1, 2b.6, 3.63 is a solved problem, 3a.1, 36.4. It's from Bird Stewart Lightfoot's book. Okay. Solve these problems for yourself, then it will be very clear to you. So we are going to stop in this lecture. Next lecture we are going to continue a little bit about turbulent flows, but we are also going to talk about a little bit about laminar flows. We are first of all going to look at little bit more complicated problems, not the problems where we had nice first order or second order differential equation. We are going to look at some more complicated situations because they are very important in real life. So that's coming in the next lecture.